to send this to myself.
How's it going?
Firefox was closed for some reason. So we are going to. Come on.
I think it's because you're on this side, kind of, so it's like right-clicking it.
Ah, jeez.
Do you want me to try?
Yeah, can you give it a shot? We just need to get the embed link, and then we'll embed it into the ACAST website.
Man, I don't know why it does this thing.
Can you just write that down?
I've got a pencil. If I can just, thanks. Oh, thanks. Okay, 0FH. Oh my gosh. That's so weird. Okay, HLG. T9A.
Capital 9A.
JJW.
Okay. So you can go ahead and start the broadcast.
Okay, so once again, Yang Liu from Emory University. Wildfire.
Sorry about the technical glitch. So I'm going to talk about our evaluation of the satellite-based fire products in the southeastern U.S. And this is okay. I ran into this problem. I don't know what happened up there, but the work is motivated by the process that EPA makes the fire emission inventories. One of the primary sort of preprocessor for the for EPA's NEI is Smart Fire. This is, I think, developed by Sonoma Tech. So Smart Fire now in version 2 uses 3 major inputs to generate the fire emission inventories. One is the MTBS, which is a landside-based burn scars measurements. Second is the ICS 209, which is the ground fire reports. And the third one is NOAA hazard mapping system. This is based on the satellite measurements of active fire counts. And I will focus on the HMS because HMS has the most comprehensive coverage. So the HMS system has been evaluated, and the work was published in 2011. And this is kind of the essence of the paper done by the NOAA team. Essentially, the detection rate drops, or the detection rate is related to the size of the burn scar. In this case, the burn scar is calculated from the ICS 209 reports. But the problem is ICS 209, this NFI, the National Fire Inventory, only covers parts of the photos. Okay. As you can see, when the fire size, the actual burn scar size drop to below like 1 square kilometer, this is still quite a large fire. The burn scar is 1 square kilometer. The detection rate is below 40%. Now, at a national level, this isn't that big of a deal because small fires only account for less than 5% of the primary emissions. Now, you can see the distribution of the ground cases in this map from the 2005 NFI. And in Georgia or in southeastern U.S. in general, there are very few cases because the fires there are much smaller than the big ones in the Sierra Nevada and Colorado. And from the EPA 2011, this is published NEI version 1, currently online. Nationwide, you can see the area burned and say the Georgia numbers, probably 9% of the total area burned. Primary PM emissions about 6% in terms of the total national emissions. So the research question is, in Georgia and in southeastern U.S. in general, we have a lot of small fires. And how good is HMS in this region? Well, that's kind of the research objective. And we've done preliminary analysis before. I've reported case studies using more detailed military-based data in Georgia. Here, we collaborated with Georgia EPD to get their custom 2011 fire emission inventory. And what we did is to pair up the ground, sort of the bottom-up data records with the top-down HMS data on a kind of standard CMAQ 12-kilometer grid. And we are trying to get the fire detection rates at the grid cell level, percentage of fires detected by HMS. And here we only attempted to evaluate fire counts. We didn't consider burn areas, fuel types, emission factors, etc. And the additional steps in generating the emission inventory. Okay. So first, let's look at the ground data from Georgia EPD. The fire counts, they come in 4 different geocoding types, and type 3 and 4, the quality is a little bit low because they set the center of the fire at the city center or the county central. Basically, these types cannot be used for spatial matching. And you can see the fire types, number counts distributions. Most of the wildfires have lead lung information. Right? Most of the prescribed burns in Georgia has this zip code level geocoding information. So basically, this is the center of the zip code. Probably okay for the 12-kilometer CMAQ grid matching. Right? We go down to 4, this is also problematic. But you can see in Georgia, most sort of the bulk of the fires are actually prescribed burns, smaller, much smaller fire. Okay. Now, high-quality counts across different land cover types. This is the NLCD 2006 land cover type. And you can see the type 0, 1, 2 counts are normally like 85 to 90% of the total counts across the different land cover types. For developed types, we have lower counts because of those type 3 and 4. They're registered to the center of the city or the center of the county, which are normally or typically populated. Okay? So monthly fire statistics. So the bars are for numbers, and the lines are for burn areas. This is reported burn areas, or the upper bound of those burn areas. Okay? When a fire permit is issued, that is the maximum amount of acres you can burn. But most likely people don't burn to the maximum amount. Okay? So by months, we can see most of the prescribed burns. Well, first of all, you have wildfires year-round in Georgia. Most of them are here in terms of number, but in terms of size, they're in spring and early summer and have bigger wildfires. Now, in terms of prescribed burns, we have most of them actually in winter and in spring, both winter and spring. This is the spatial distribution of the Georgia EPD counts in terms of prescribed burn. You can see they're all over the place, all over the place. 36, about 28,000 in total per year. A little bit more concentrated in southwestern Georgia, primarily in winter and spring. Wildfires has a more sort of spread out distribution than the prescribed burn. And now we go to the HMS with the satellite raw seasonal pixel count. This is not the actual fires, because for larger fires, you have multiple pixels processed together. Before we process the HMS data, and this is presented by season. And you can see HMS picks up the spring fires much better than winter. You compare with the ground data, HMS is actually missing a lot of fires in winter. Is that due to cloud cover? I don't know yet. We haven't looked at the cloud data. It needs further investigation. So after processing, after clustering all the raw HMS pixels, we calculated this figure in a similar format to the 2011 IEEE transaction paper. And the top line connecting the squares, this is the combined HMS detection rate. As you can see, the scale here is much, much smaller than the 2011 paper. It starts from about 10 square kilometers all the way down to less than 0.1 square kilometers. And you can see the detection rate when it goes below 0.1 is less than 20%. The mean for the fire size is about 10 to 28. That is 0.05 to 0.1 square kilometers. Very, very small fire. Okay. And we try to aggregate them to the 12-kilometer CMAQ grid. This is the Georgia EPD fire counts on the 12-kilometer grid cells. And you can see it's going to here, some here. This is Metro Atlanta, fires. This is the HMS daily fire counts, much lower than the scale. And if we calculate the raw ratios, this is still work in progress. It's very sporadic. So there is no, I can't say there's a pattern. Maybe because the count is too low. So when you divide a small number by another relatively small number, you get large or uneven distribution of ratio. And we're continuing to work on this. One thing I learned from this process is fire is a very messy business. Lots of data issues to deal with. So in summary, we see that HMS in general detects 20 to 30% of fires, and seasonal-wise, you have to rely on ground data to somewhat correct it. And just for reference, the Georgia EPD custom inventory is different from the 2011 national inventory by about 10% of total fire counts and 20% in prescribed versus wildfires, if you have to categorize those. So the 2011 national inventory overestimates wildfires by 2,000 fires and underestimates prescribed burns by 4,000. Right? So that's roughly 20% on each side. And when it cancels each other, when the two cancel each other, in total, the national inventory is about 10% lower. On count, not in terms of area. We haven't done those things yet. And in terms of next steps, we will work with the Georgia EPD to create more robust grid cell level calibration ratios for fire emissions in the southeastern region. And the reason that we do this is to generalize. Georgia in general has a much stronger technical capabilities in terms of CMAQ modeling. Georgia is actually modeling the entire southeastern region on behalf of other states. That implies that the other states may not have as accurate emission inventories as Georgia. Okay? So we hope to get this sort of ratios and then evaluate them and then extrapolate or generalize for the entire southeastern region. And then we'll compare the CMAQ runs using this calibrated fire emissions with the standard EPA NDI runs and the Georgia EPD custom runs at 12 kilometers. And also, we also want to evaluate the satellite measurement error. There are issues with HMIS, especially related to the geo-registration issues and multiple count or multiple sensors. They have duplicates that cannot even be teased out by their human elements. But we can sort of get an idea from the GPS quality data from Fort Stewart, one of the Army bases in Georgia. And we want to evaluate the other emission inventories that we have access to, including GFAT3 and FIN. Just to show you some preliminary data, this is GFAT3 at half a degree resolution for the southeastern US. This is FIN at the same spatial resolution southeastern US. Now GFAT3 is based on burn scars. FIN is based on active fire spots. And you can see the difference. It seems that FIN does a lot better job in the southeast than GFAT3. This is, again, work in progress, and we'll continue to work on this. And that's it.
You know, it's interesting from people developing with perspective, trying to differentiate Strive versus wildfires. The reason is, you know, the problems is one question, but also the emission characteristics are different.
Very different.
Wildfires burn more water, emissions go higher in the atmosphere, and you get things out of it. So trying to get that split on the key aspects, trying to improve. Then another question, which is, have you guys also sort of look at agricultural fires? I don't know whether that's their missions, but is that also work? That's another area that you're not research in, and also again trying to get mission characteristics.
Yeah, we only did very preliminary, very rough analysis in that this case. So cultivated, there are roughly 6,000. That's about 1/6 of the total prescribed burns over cropland. We haven't done anything more detailed than this, because we would need extensive grounded support to get something useful out of it. But yeah, there's a lot of agricultural burns. Yeah.
Maybe one more.
HMS needs to have kind of a flag to identify flares, and for HMS distribution seemed to throughout the year had 2 hotspots. And you try to look at characteristics of those particular regions. So I guess spring, winter, there's those 2 regions that stand out. Those, you look at those in detail and you talk to HMS about how they kind of have an ad hoc way of identifying persistence.
Yeah, I haven't talked to them yet. I hope I can get in touch with Mark a little bit more to get more detailed information.
Okay, we should move on. The next talk is by Kevin Wecht of Staff Harvard. He's talking about high spatial resolution methane. Kevin?
Thank you, David. My name is Kevin Wecht.
Oh, sorry. Oh,
My name is Kevin Wecht. Good. Hi, my name is still Kevin Wecht. I am a postdoc in the atmospheric chemistry modeling group here at Harvard. And I did notice on the agenda there are no other talks with methane or CH4 in the title. So if you're interested in methane, you have to listen to me. And if you're not, hopefully I can change your mind or at least pique your interest a little bit, because I think we're making a lot of interesting developments in observing methane emissions from space in this group. And the future is bright for these applications. So first of all, methane globally has a radiative forcing emissions of methane have a radiative forcing over half that of CO2 emissions. Methane has a shorter lifetime than CO2, which means it can be a shorter term lever for mitigating climate change. On a 20-year horizon, the climate impact of global methane emissions is comparable to that of CO2. There are some nice air quality co-benefits of regulating methane emissions, namely that doing so would decrease background ozone concentrations because the oxidation process of methane leads to ozone creation. And finally, methane may be cheap to control, but that's only if we know what to control. Now, there are a lot of sources of methane to the atmosphere, both the natural and anthropogenic. Methane comes from the fossil fuel industry, from oil, gas, and coal. It comes from agriculture by way of rice cultivation, livestock, and cattle, and hog farming especially. It comes from waste management and landfills and wastewater treatment. And there's large uncertainty associated with the magnitudes of each of those sources that I just described. So designing some kind of intelligent emissions mitigation strategy depends on better understanding those sources. We don't want to waste our time going after one source just to find out it wasn't nearly as important as we thought it was. So better understanding of emissions is key to designing more effective emission control policies for methane. And there are two means by which methane emissions are often estimated. The so-called bottom-up, where we take some very small-scale information and try to extrapolate, for example, how much methane comes from a single cow. That information, in combination with a gridded map of cattle density, demonstrated on the left, could give you a global map of methane emissions from cattle. In this type of approach, though in much more sophistication, is what's often used by regulatory agencies such as the EPA in devising their methane emission strategies. On the other hand, we have the so-called top-down approaches, where we can make observations of atmospheric methane, and we can infer what emissions must have been in order to match the atmospheric observations that we make. Here in the atmospheric chemistry modeling group at Harvard, we're interested in combining information from both of these approaches, and specifically using satellites and asking what kind of emission constraints can satellites provide in combination with suborbital observations of atmospheric methane over North America. Now, North America, like global emissions, North America emissions are quite poorly characterized. They are thought to represent about 10 to 15% of global emissions, and the source distribution roughly reflects that globally, though with fewer emissions from rice. Like with global emissions, uncertainty abounds in emissions, our understanding of emissions from North America. On the right side, you see a pie chart that represents an estimate of US anthropogenic emissions from the EPA, colored by source category. The two largest sources are from livestock, that's both cattle and hogs are the dominant pieces of blue in that plot, and oil and gas is also of comparable magnitude according to the EPA. Now, numerous surface and aircraft studies have suggested that both the total emissions from the EPA as well as the source type attribution or allocation between these various sources is uncertain by up to a factor of 2. That's significant. I think you'll all agree for doing something about our emissions. And we want to know if satellites can add anything to this conversation. If we can use satellites to provide some high-resolution spatial constraints on emissions across North America, including the United States, to better resolve some of these discrepancies. Satellite observations of methane can be derived from observations of thermal infrared radiation, as well as from shortwave infrared radiation. The thermal infrared used by satellite or instruments such as AIRS, TESS, and YASI generally gives sensitivity in the mid to upper troposphere and isn't of great utility for constraining sources that are at the surface, at the bottom of the atmosphere, of course. For that purpose, shortwave infrared observations from instruments such as SKIA-MACHI, launched by the European Space Agency in 2002, and by GOSAT, launched by the Japanese Space Agency in 2009, are of more promise. Again, our goal here in this group is to apply these shortwave infrared satellite observations to obtain high-resolution emission constraints across North America, and very importantly, in the process, inform the bottom-up inventories on which policy decisions are made, and also pave the way and enable this same type of work to be performed from the next generation of methane-observing satellites that will have even better and greater capabilities than those flying today. So let me tell you about our first application and foray into this field. This is using SKIA-MACHI observations, that instrument launched by the European Space Agency. Uses these observations in the summer of 2004, shown in the top right, in combination with a bottom-up inventory provided by the EDGAR, many of you may be familiar with, shown in the top left. We use these two pieces of information in combination with the GEOSCHEM chemical transport model and its adjoint at 1/2 by 2/3 degree resolution over North America in the domain showed in these plots. And we ultimately, at the end of this study, get a map of gridded, optimized methane emissions across this domain. We can use suborbital observations from aircraft to validate the satellites and to evaluate the inversion corrections performed throughout this process. But of primary interest is this resulting map, this gridded distribution of methane emissions across the North American continent. In the top left, you'll see the prior map that we started with. This was constructed just from the bottom-up information, not by us, but from a number of sources that we've simply compiled and used in GeoSChem. The top right represents our optimized emissions after we apply the Skiamaki observations in an inverse modeling framework. And the map on the bottom left shows a ratio between the two. You can see large blue swaths across Canada. These are in wetland regions and tell us that the emission inventory we were previously using was too high in those regions. The Skiamaki observations are telling us to lower emissions across these large wetland areas. Conversely, there are large red regions across the center of the United States where the satellite data are telling us that emissions need to be greater. They need to be stronger in order to better match the observations. We ultimately find a horizontal spatial resolution of about 100 by 100 square kilometers over this domain. And we can start to use a map like this to inform air quality managers and policymakers. And the key step here is applying our optimized emissions field and kind of segregating it by emission categories. So for example, we can take our prior distribution of livestock emissions, shown in the bottom left here. We can apply our optimized correction factors from this procedure, and what we'll get as a result is a kind of optimized, or an updated rather, map of livestock emissions across North America. We do this for all the different source types, and this pie chart on the left shows the resulting source attribution or source allocation across North America from our study. Next to it on the right is a pie chart from the EPA representing their estimate during the same time period. In total, these numbers are similar. You can see in the very top there, they're within a less than 10% difference from each other, but there are larger differences in our attribution to source types. For example, we find livestock emissions to be the largest single source in the United States, and oil and gas to be of less significance. Though to some degree this may reflect a shift, a shift from methane emissions associated with oil and gas distribution through pipelines and end usage towards emissions from locations of extraction and mining itself. Now, of great importance, and what's really, I don't know, one of the more exciting applications of this is taking our work and informing people who may actually use it for policy purposes. And Melissa Sulprizio at Harvard in the back there has started to do this, engaging stakeholders in the state of New York and also in Iowa to evaluate their estimates of their own methane emissions for their greenhouse gas inventories. Here's an example of zooming in on the optimized correction factors I've already shown, but just over the state of New York. And from this analysis, we suggest that the methane emissions in our prior inventory overestimated methane from New York by a factor of 0.6. And very interestingly, there's a very, very large emission source in Western New York in neighboring Canada. It's associated with oil and gas distribution and also with landfills that just doesn't seem to be observed by Skiamaki. And you can see these dark blues show that that region is being pulled down quite strongly in our analysis. Melissa is also working with the state of Iowa, in which our main result has been that livestock emissions associated with either cattle or hog farming, those emissions are underestimated in the prior inventory. Now, I want to take a minute to talk about hydraulic fracturing, or fracking as it's commonly called. Fracking is a process by which rocks are actually fractured, they're broken apart in order to enable natural gas to flow more easily to a nearby well, where it's then extracted and processed and used in all the ways that we do so today. Recent technological developments have lowered the cost of this process and basically made its frequency and its usage in the country skyrocket recently. In 2005, less than 5% of US natural gas production was produced via this fracking method. By 2010, it had increased to 23%, and in the next 20 years, it's projected to account for about half of all natural gas production in the United States. Now, this is important because we are starting in this country to switch from a dependence on coal for electricity generation to a dependence on natural gas. This has started largely by these new fracking procedures, and I think you see some policy developments that may be really cementing this in place. Basically, fracking is here and it's going to be here to stay. In order to reduce US greenhouse gas emissions by 30%, as the president had recently proposed, we're going to have to transition from coal to natural gas, which has a higher energy content per atom of carbon, meaning lower CO2 emissions. However, if there are fugitive methane emissions associated with the extraction of natural gas through fracking, this may offset some of the climate benefit that we achieve by switching from coal to natural gas. So this is why people are interested in quantifying methane emissions from fracking. Now, it's also becoming increasingly apparent that emissions from the natural gas and oil industry, especially at extraction sites, are highly variable in time and space. Wells aren't emitting at a slow, constant rate evenly across the country. Instead, they seem to be emitting sporadically in both time and location, possibly associated with regular well operations. However, this is hard to monitor with the current in situ observing capabilities, and satellites, therefore, with their vast spatial coverage, represent a potentially huge source of information and a method to more effectively monitor emissions from fracking and from gas and oil in general. Now, sadly, the instrument used in this study I've shown has fallen out of the sky. I think as someone mentioned earlier, David maybe. But we have GOSAT, launched by the Japanese Space Agency, which is still operating. It provides precise but sparse measurements of methane. And very excitingly, in 2015, TROPE-OMI will be launched by the European Space Agency. It will provide much greater coverage, horizontal resolution, and precision than anything we've been able to use today between SCIAMACHI and GOSAT. In some synthetic experiments with synthetic data over the state of California suggest that the observations may be able to achieve observing capabilities similar to that of a 2-month dedicated aircraft campaign over the state. So having that kind of coverage and that kind of information across the whole continent at all times of year and hopefully for many years will really be a revolution in our ability to monitor methane emissions from space. And at least here in the group, we're just really excited about this prospect, and I think we've kind of paved some roads to take advantage of those new data sets coming in. So with that, I'll thank you for your time. Take any questions if I have time. Thank you.
I just wondered if you mentioned the infrared information and unable to obviously see that surface and then
yeah.
they're not very good for doing the emissions directly. But in combination, say with SCIAMACHI, have you tried to use the two together to get in fact better information from the surface?
Yeah, we haven't for the study I've shown. What we have done is looked at the combination of TESS, which is a thermal infrared observing instrument, and GOSAT over California. And there, part of this is because TESS observations are also sparse, but we do find it useful for constraining kind of a background state and kind of truing the model to a free tropospheric concentration before using the total column measurements from shortwave infrared. I think with maybe thermal infrared observations with greater spatial coverage, maybe like from AIRS, could or YASI, could be useful.
Okay, we've got to move on. Thanks, Kevin.
Thank you.
Our next speaker is Deborah College from Western Maryland, who's going to give an update and further elaborate on emissions from oil and gas extraction.
Thank you very much. So yes, today I'm actually going to be giving kind of an overview of some of the progress that has taken place so far with this newly funded Tiger Team project, focusing on satellite signatures of trace gases associated with oil and gas extraction. The lead PI for this project is Ann Thompson, and we have several ACAST participants that I'll be showing a little bit of a snippet of work from each of them so far. Okay, so as Danielle had said, kind of the focus of Tiger Team activities is to address current issues that air quality managers are looking to get answers about, and so one of which is about these growing oil and natural gas operations. And one question was, they really wanted to get an idea of what were the trace gases doing in and around and downwind of these operations. And they also wanted to know if satellite observations would be helpful to check their newly modified emissions inventories. And so we're working with several air quality managers on the local, regional, and basis, including Maryland and Colorado, as well as Marama and Sensera and the EPA. And our approach for this project is to be able to supply satellite products to the policy stakeholders to look at 4 focus regions. We also wanted to make sure that these products are sufficient in terms of their sensitivity, so we are validating some of these products with available ground and aircraft trace gas measurements, and we also have activities where we are taking those products and comparing them to emissions inventories and air quality modeling that's taking place. So this is just a table showing some of the goals that each ACAST member is looking to accomplish. I won't go into this into detail, but this is some of the work that each one is looking to address, and we're focusing on 4 areas across the U.S., each of which contains some of the major basins where oil and natural gas operations take place, including the Marcellus Shale in the east, the Williston Basin in the north, the Utah, Colorado, Wyoming region, and also looking at, in the south, Texas and Oklahoma. So as I go through this talk, I just want to give an update from some of our team members, and so I wanted to start with some of the work that Ann Thompson and myself are doing, and we are looking at methane. So actually Kevin's talk was a nice intro to some of the issues that are present with looking at methane from satellites, some of the satellite instruments that you can look at for looking at methane in these areas. And so here we actually want to kind of identify some of the changes in methane from region to region, looking at the east and the western U.S. And we are also looking not just with satellite data, but we also want to get an idea of the horizontal and spatial variabilities in each of these regions, looking at in situ measurements from campaigns like NASA's Discover AQ campaign, which had one part was in Maryland in 2011. In 2013, there was the California and Texas deployments, and upcoming in this July, August, there will be in situ ground and aircraft measurements in the Colorado region. So our first step was to look at some of this in situ and aircraft measurements and take a look at how the satellite observations compare. And next is to take those time series that we have from these satellite observations and compare them to some of the things that our air quality folks are seeing. So starting with the ground and working our way up. So Ann Thompson has the Penn State native trailer that gets deployed during the Discover AQ campaigns. And we have observations of methane and its isotopes during the California and Texas portions of the campaigns. And we actually see the differences between where Native was situated in Porterville, California versus Smith Point, Texas. We actually can identify with the use of these isotopes some of these sources for methane and in these regions. So on the left, this is actually time series for methane and carbon dioxide at Porterville, California. And on the right, we have methane and carbon dioxide for Smith Point, Texas. And we wanted to take a look at, see, and identify what some of the sources would be for these peaks, these spikes in methane during the time period. And we actually find that in Porterville, California, there was more of a signature from oil and gas operations versus Smith Point along the Gulf Coast, which actually had more so of a wetland biogenic emission signature. And if we then move up in the vertical, we can take a look at some of the aircraft profiles that were done during the California portion of Discover AQ. And we also, again, can kind of point out variability from one site to another based on looking at various trace gases. So this right here is a map of some of the regions where the P-3B aircraft was profiling. The point that's further south is Bakersfield, and north is Fresno, and we have Porterville. And so on the left here we have from top to bottom we have distributions of methane in the vertical. This is nitrogen dioxide and ammonia measured from the P3B, and this is for Bakersfield, and on the right is Porterville. And we find that based on the relationship, some of the concentrations that we're seeing closer to the surface, that you really could identify that the methane being measured over Bakersfield was more of an oil and natural gas derived source than, say, over Porterville, which had a lot higher concentrations of ammonia, and there were lots of farms located near Porterville, California. So we see more of an agriculture source for methane at Porterville. And with this in mind, we want to then take what we are learning and see how the satellites compare. And so there's been discussion on infrared versus shortwave, and so I've actually been looking at tests observations, which, as we've heard, is more of a background in free tropospheric value for methane. But to me, there's still some valuable information in terms of improving those emissions being modeled, because we definitely identify Bakersfield, which just south of Bakersfield and in and around Bakersfield there are several oil and gas wells, versus towards the north, Fresno, where there are hardly any. So we're definitely seeing that spatial variability just in one test transect in terms of methane concentrations, and that's just in kind of a free tropospheric air. So, and so far we've looked at TESS and P3B profiles, and we see pretty reasonable correlation above the boundary layer. I won't spend too much time on this part, but this is, we're looking at kind of west versus east, and we're looking at 2008 versus 2011 and getting an idea of how background methane has been increasing in those regions, and we are also starting to complete some of the validation for the Maryland portion of the Discover campaign. So on to some of our other ACAS participants. Daniel Jacobs' group is looking at other satellite observations, as we've heard, and so one of which is GOSAT. So the figure on the bottom left here shows a map of GOSAT averaged over 2009 to 2012, and as we can see here, very similar to what Kevin had shown for Skiamaki, there's definitely some sensitivity for GOSAT to regions where we have oil and gas basins. Also in this group, we have Li Zhu, who's looking at formaldehyde, as we actually heard a little bit earlier. And so we're trying to use formaldehyde to distinguish between oil and gas operations and other sources of methane. And this example is in the kind of Houston, Texas, and Fort Worth region. And we've seen this slide too, but I just wanted to point out that some of our other collaborators include Dave Edwards and Gabby Pfister, who are part of the FRAPPE campaign, which is going to be going on concurrently with the fourth deployment of Discover, as I mentioned, in July this year. And so we are working together to characterize those emissions from oil and gas in the Colorado area. We also have collaborators at the University of Colorado Boulder. Jenna Milford and Devin Hensey are linked to the Air, Water, Gas Sustainability Research Network, and they're helping us to interpret Western oil and gas emissions. And just to kind of also point out some of the other updates from our Tiger team, Brad Pierce is coming up next, and he will be looking at spatially enhanced OMI NO2 columns and evaluating those versus emission inventories. And he'll also be showing some work with using the VIIRS day-night band. And Russ Dickerson, who is also on our Tiger team, will be talking about Maryland measurements on Wednesday. And one of his members of his group are actually looking at some of the long-term sites that are in Maryland to identify when possibly there could have been some sort of downwind contribution from oil and gas operations starting in, say, the 2011 time period, looking at ethane concentrations. So I will stop there and just point out that we have several team members that are participating in the upcoming FRAPPE and Discover AQ missions in the Denver Front Range region. And so we'll have lots of observations to compare with the satellite products that we're looking at.
I'm wondering, have you looked at not only in oil and gas producing areas,
Yes.
let's say, some of that may be happening without any oil and gas production in those areas.
Yes.
But also interested in knowing what methane levels might be, let's say, to the mid-latitude average.
Yes.
Even in a remote area, what are you really doing to the overall trend of mid-latitude?
Right. So when we are actually looking at, we're going to be doing the 2008 versus 2011 comparisons, we're also going to be looking at background. So not just looking at the regions where there actually are the operations, but what's the background during that time period. So, yeah.
Thank you. Thanks, Deborah.
Yeah.
My third question. Within the oil and natural gas, if I was going to split oil and natural gas into categories,
Yep.
and then looked at, say, Pennsylvania, South and Alabama, mostly gas.
Yep.
And then to North Dakota, it's mostly oil and gas there.
Yes.
As we speak. So are you able to do these kind of studies to differentiate the ethnic signature and
Yes, so that's exactly what we want to do and we want to do it for the two different time frames. So 2008, say, versus 2011, and looking at actually what's going on between there. Keeping in mind when I was talking about tests, it's just background concentration. So you need to bring in something like GOSET to get an idea of what's going on, in the closer to the boundary layer.
So are you able to pick up the signature of the and orange, like the census area in Dakota versus South?
On the east, it's kind of tough because there's other sources. But I definitely have, looked in kind of the Williston Basin region, and you can definitely see a signature. I'm not quite sure yet whether we can distinguish between the two different types. So.
There's no comment on that. One of the things that we're looking at is trying to use some of the thermal banners that are doing fire detection to identify. And so associate the column measurement of the trace gas and see if we can identify signatures of fire that are
Okay. So thanks, Deborah. We'll let Brad continue the two columns of the oil and gas.
Okay, I'm standing between you and lunch, and we're one talk behind. So as Deborah said, the focus of my particular task within this Tiger team is NO2, and particularly seeing whether or not we can get a spatially enhanced OMI NO2 retrieval by taking advantage of high-resolution measurements from the VIIRS day-night band, which is a new, VIIRS is the follow-on to MODIS, and it has a very accurate day-night band that's a follow-on to the DSP nighttime lights, and so we'll be talking about that today. The objective of this, we've seen that with OMI NO2, David's work and Brian's work, that you can do trend analysis very accurately. We've seen that we can associate to very high correlation the overall emissions within an urban area between the NEI estimates and the column. And what we're trying to do here is see whether we can push things further and start trying to understand some spatial variance within urban areas first as a test case, which are well constrained with the emission inventories, and then look to see whether we can apply it for oil and gas, which is less constrained, and see if we can look at its variability. Again, figure here kind of to give a motivation. On the left, we have the distribution of these various oil shales and the production regions. On the right, we have NEI 2011 emissions from oil and gas that were put together by Stu McKeen at Esrael and will be used in this study. So Again, this is a work in progress, so I'm going to go through the steps that we've accomplished so far. To begin with, we've been working with Western Regional Air Partnership, Tom Moore in particular, to say to what extent can we use the current OMI standard product, standard pixel resolution, to understand the variance of the spatial variance of NO2 column compared with emissions for specific geographic regions. We identify what we're using is the OMI Berkeley High Resolution Retrieval that's developed by Ron Cohn's group. It's got some advantages over the NASA standard product in some of the APR information it takes in. And we're looking at this at a resolution of the native resolution, which is 13 by 24 kilometers. So we identify regions of interest. We aggregate the high-resolution RAP Phase 2 emission inventory onto the OMI footprint on an instantaneous overpass basis, and then we can conduct statistical analysis to see what the information content is over a specific geographic region. So we're trying to push the data further than some of the trend studies that have been established before. This is a slide showing the RAP NO2 emissions that were used in the WestJump air quality modeling study. It's a 4-kilometer emission data set. It's been highly vetted and used within assessment activities, and it was provided by Tom Moore of RAP. And here I've identified a number of different geographic regions that we're focusing on, including some urban areas such as Salt Lake City, Phoenix, Denver, some purely oil and gas regions as identified by the RAP emission inventory, and then some background regions to see what our level of detection is. So the analysis is illustrated here for a particular region, the Denver and Denver-Julesburg Basin, which is a combination of urban and oil and gas emissions. On the upper right, we have a PDF of the RAP Phase 2 emission inventory aggregated onto the OMI footprint. The white line is the distribution of the total emissions, and the red is showing that part of it, which is oil and gas. You can see for this particular area, it's both urban and oil and gas. The bottom figure on the left-hand side shows the OMI BER distribution, and you can see that it is not capturing the spatial distribution of the observed emissions. If we actually look at the correlation, which is the figure on the lower right-hand side, we do get a fairly good correlation. Hard to read both of these. Sorry, it doesn't show up very well at all. We get a correlation of about 0.4 linear correlation for this particular region when we aggregate that high-resolution emissions onto the OMI footprint. This is an example now for one of the oil and gas basins in the western U.S. In this case, it's dominated by oil and gas emissions, and we get a slightly lower correlation, but it's still something that I think is worthwhile. It's a correlation of about 0.34. To summarize this comparison, this is showing each one of those different regions that we selected based on the RAP emission inventory. The reds are either urban or oil and gas basins. The blacks are background regions. And you can see that for background regions and a fair number of the oil and gas regions, we really have very little correlation with the emission inventory and the OMI NO2. Whether that's because the emissions are below the level of detection of the OMI instrument or uncertainties in the emissions inventory is what we're trying to untangle. We're kind of setting a threshold of about 0.3 correlation for this part of the study. And in that case, we can see that in urban areas, we have what I would consider reasonable correlations, and that for some of the oil and gas regions, we have some information from the OMI at the native resolution. So the second step is now to take this and extend this over the continental U.S. and to go to 2011 NEI and see how robust that is and whether we can take the results from the RAP emission inventory and use those in the eastern U.S. as well. So we're doing the same analysis. In this case, we're using a gridded modeled NO emission from WRF-Chem modeling framework that was developed by Stu McKean, and using that to evaluate the OMI at the native footprint. So this is the distribution of the NEI 2011. In this case, it's NO emissions. And again, now we've taken the same regions in the western U.S. and we're expanding that into the eastern U.S. using the emission inventory with and without oil and gas to identify regions of particular interest from an oil and gas perspective. And so we've added to our list of regions that we're focusing on this set of oil and gas regions. In some cases, in the eastern U.S., a lot of the regions are much more extensive. So for example, for the Marcellus, we've broken that up into 3 different regions, a southern, a central, and a northern region based on the NEI 2011 emission inventory. Same thing for the Haynesville in eastern Texas. We've added 3 additional urban areas, Atlanta, St. Louis, and Minneapolis, to give a constraint on how things compare in relatively well-constrained emissions. And these are the summary of the results now expanded to include the whole continental U.S., and it's for 2011. What you can see here, if we set that threshold of 0.3, is that we've got a significant reduction in the correlation between OMI and the NEI 2011 emission inventory than we did between OMI and the RAP, even in the western U.S. That points to, I think, 2 different things. NEI 2011 is recently developed. The emission inventory for Wharf Chem, the gridded model emission inventory, was just generated in late March and hasn't really been evaluated within a full modeling framework, so there's that uncertainty. And then secondly, as we've heard, as we move into 2011, we've got row anomalies in the OMI instrument, and that's going to affect our statistics. So the results for 2011 are somewhat less favorable than they were in 2008, but we'll continue to move forward. And the next part of this is where we're trying to now bring in some additional satellite information. And what we're using here is the VIIRS day-night band. So this is a very high accuracy, very low intensity visible light measurement that's done by VIIRS at a very high spatial resolution. So the resolution of these measurements is 700 meters. That's been aggregated onto a 16th of a arcsecond global grid by the NOAA National Geophysical Data Center, and we're using that data set, which was put together compositing cloud-cleared day-night band lights for a period in 2012, and we're using that to look at and comparing that with the NEI 2011. So this is the distribution we get. It's the same geographic regions that we defined for NEI 2011, and you can see that there is spatially a very high correlation overall between these 2 different data sets. And what we find, again, for each one of these regions is we can now look at the spatial correlation between NEI 2011 and the VIIRS day-night band, and now we can see that we get very high correlations. In this case, what we're doing is we're actually aggregating the VIIRS day-night band data into the NEI 2011 4-kilometer footprint because it's higher resolution, and we're able to get correlations that are up around 0.6 or so for most of the urban areas, and we're also starting to bring out a number of the different oil and gas regions. So this has promise that we can use this measurement as a proxy for NO2 emissions. This is just an example, again, of how we go about doing that. This is for the Burnett region, and again, this is a region that's dominated by oil and gas production, but there is a contribution from anthropogenic sources, and you can see now when we compare NEI 2011 for this particular region, we get a correlation that's up around 0.6. This is one for Atlanta, and the correlation, again, shows a very compact relationship between the VIIRS day-night band and the NEI 2011 emissions. So the final step and the main objective of this particular Tiger Team activity is to now use that VIIRS day-night band radiance, which is at a very high spatial resolution, and we've shown that it's correlated with the NEI 2011 emissions, and use that to repartition the OMI NO2 that's retrieved in the large footprint into smaller footprints. So this is just illustrated here. We'll focus on Atlanta. This is the distribution of the day-night band over Atlanta. This is the OMI, a nominal OMI swath over the top of that with large footprints. We break that up into a 4x8 subset, so roughly 4 kilometer by 4 kilometer footprint. And within each one of those pixels, we compute the aggregated VIIRS day-night band.
in that subpixel. We add those up for all subpixels and get a mean for the OMI footprint. And then for the entire swath, we look at the correlation between the Beers day-night band and the OMI footprint, and that gives us a linear regression that allows us to redistribute that large OMI footprint NO2 mean over the different boxes. And that's illustrated again for a particular orbit. This is Atlanta on July 24th, 2011. In the upper left, we've got the native OMI burr retrieval over Atlanta. In the lower left, we've got the aggregated day-night band on this OMI subpixel. And then in the upper right, we've got the redistributed OMI pixel. And you can see that now we're picking up information at a scale much finer than the original OMI retrieval that's reflected in the Beers day-night band. The lower left scatter plot is just showing the correlation between the correlation between the mean NO2 and the Beers day-night band for that entire swath. Another example, this is now for New York. Again, we've got the native OMI footprint on the left-hand side, much too coarse to try and inform urban NO2 emissions, but we can project the Beers day-night band aggregated on the OMI footprint, and now we're able to pick up structure within the Manhattan area, and again show a very compact relationship between the Beers day-night band for that OMI orbit and the OMI NO2. So again, this is a work in progress. What we can summarize at this point is that the OMI bear NO2 retrieval shows reasonable correlations in 2008 for western U.S. Urban regions and some oil and gas regions in the western U.S. OMI bear NO2 shows reduced correlations compared with NEI 2011 in the western U.S. and also in the eastern U.S. But the Beers day-night band shows a quite high correlation with NEI 2011, and we can use this information to try and enhance the use of the OMI data at the smaller footprint. So the next steps of this, the kind of the main objective here is to develop a satellite retrieval that is at the scale of the regional air quality model grid so that you can use this to constrain emissions. You can't really do that with the coarse resolution of the OMI measurement itself. So we'll be doing that, using this to evaluate both WRF-Chem and NAM-CMAC air quality predictions during the 2011 Discovery AQ mission. And then we'll be taking this to the field during FRAPPE and be able to evaluate application of this to the OMI standard product with both airborne in situ and remote geotasso NO2 measurements. And I think you'll hear follow-up about the Discovery AQ. This is part of the reanalysis project. You also hear about some of the geotasso measurements in subsequent talks. I'll stop there.
Maybe just one quick question.
How well you're getting spatial distribution within the box.
Exactly.
Equally, a really important question would be how well you're getting the ratio. Like I'm in Texas, I want to know what's the ratio between how much by shale and from the shale. So, what are you doing to look at whether you're getting things right in terms of volume, not positive?
So I think that is yeah. At this point, what we're doing is, can we look at sub-regions instead of looking at continental U.S. as a whole? I think we've established that we can do that to some degree, and maybe now the next step is to now look at NO2 column 2 emission ratios to see whether we can see differences between different regions, like you're suggesting.
Yes, Dave. Okay, lunch. Yes. There's a few options. The most obvious one for the optical area, take the right out of the building and you kind of go along its a couple buildings away where you'll see outdoor tables and you go into the building. You follow the logo. That's actually very good at the optical area. Another option, Chinese food truck. You get out of this building on the left and you will see it right there. It's actually pretty good. If you want a good sandwich, you can go to the food called Oxford Spa by walking down the street on Oxford Street, make a left and then go up. And we have nice sandwiches. And of course, if you go to Harvard Square, you get tons of places. You got plenty of time. We're going to get back here at 1:30. The room is not secure, so take your laptop with you. And that's it. Again, for those of you who have posters, you can go ahead and put them up. I'll see you all at 1:30.
I looked one of the talks after lunch and I didn't load. I didn't know where you're showing.